involve a 5-card hand. So the denominator, they're all probability questions, and they're all a 5-card hand. So every single problem, we're ready for E and F and G and H and I and J and so on. Every problem is going to have a denominator that's 52C5. Because when we do probability, the denominator is the total. And the total number of 5-card hands in the deck is 52C5. That's it. That's going to be the denominator for every one. Now let's look at the numerator for E. The numerator is going to be the number of ways that you can get 3 jacks and 2 kings. Okay? So you must get 3 jacks. Well, how many jacks are in the deck? 4. And you must get 3 of them. So your numerator is going to start out with 4C3. Because you have to get 3 jacks and you're picking from 4. And times you need to get 2, whatever the other one was, kings. Well, how many kings are in the deck? 4. And you want 2 of them. So your numerator is 4C2. And then we can type this in. All together, you don't need parentheses and all that stuff. What you do need to pay attention to, guys, is the E at the end of the number. If you wrote down 9.234 as your answer, okay, you're still at the prom, folks. Because can a probability be 9.2? No. No. The answer is 9.2 times 10 to the negative 6. Which, if you wrote it out decimally, which you don't have to, but if you did, it would be 0.00000, right? Not very likely this is going to happen. All right. No face cards. Okay, if you want no face cards, then that means you don't want any jacks, kings, or queens, right? So let's take those out. How many of those are there? 12. So how many good cards? Those are bad cards. I don't want any of those. So how many good cards does that leave me with? 40. And I want 5 of them. So 40C5 is my numerator. 5 non-face cards. Remember, your numerator is what you have to have. So you can't have any face cards, so take them out. This is going to be better. I mean, a higher number. Did you get 0.253? So what does that mean? That means there's actually about a 25% chance that you're going to get no face cards when you're dealt face. Have all of the aces. So I'm going to deal you 5 cards, and you have all of the aces. 4C4. Because why? Because there's 4 aces and you got to have them all. But be careful. How many cards are supposed to be in your hand? Ooh, where's the other one going to come from? How many other cards are there that aren't aces? 48? And you gotta pick one, whoops, you gotta pick one of those. It's a 5-card hand. 4 of them have to be aces, but the other one can be anything else. That's your answer. That'll be another small number. Okay, I got 1.847 times 10 to the negative 5th. Anybody else get that?
Yeah.
Alright, I think I'm gonna quit taking time to type them in. Everybody getting these answers, okay? Okay, so on test day, yes, you need to type it in, but I don't wanna waste a bunch of class time doing that. Alright, where am I? H. What is the probability of being dealt a 5-card hand and having 2 10s, 2 jacks, 1 queen? Alright, 2 10s. How do I get 2 10s? 4, C, 2. Where'd the 4 come from? There's 4 10s in the deck, and you're gonna pick 2 of them, any 2. And then, so times, and 2 jacks, that will be another 4C2. And, so times, 1 queen, 4C1. All that times together, divided by 52C5. No aces, no queens, no 5s. What?
40C5.
Why?
It's the same as the face cards.
Take out the ones you don't want. There's 4 of each, right? So we're gonna take out the 12 we don't want, and 8 is exactly right. It's 40C5. Because if we take out the 3 kinds of cards we do not want, there's 40 left. And I'm gonna pick from those 40. Exactly 4 spades.
13C4.
There's 13 spades in the deck. Everybody remember that? But again, this one's one of those tricky ones because it's a 5-card hand. So this takes care of the 4 spades. Where is that 5th card coming from? The other suits, a diamond, heart, or club, right? And how many of those are there? 39. Uh-oh. What is the probability of being dealt at least 4 spades? The denominator is still 52C5. That is never going to change. In a 5-card hand, it's 52C5. If we were doing a 4-card hand, it would be 52C4, right? That never changes. I want at least 4 spades. Okay, what does that mean? What's different about this problem?
It's like
So what? So we still have 4?
yeah.
So this, we could still have this. This is 4 spades and 1 other card. So we have that. Or what else could we have? All 5 spades, which would look like,
Times 13.
yep, not times, it'll be added. Because remember, anytime you're, okay, so this is perfect, let's look at this. This is 4 spades and 1 other card. Or 5 spades. So when we're doing this and this, we're gonna multiply. When it's this or this, we add. Now, this one, when you type it in, because it's got a 2-part numerator, you're gonna have to type in the top and hit equals, and then divide it by the bottom. Okay? You're gonna have to type in the whole top, just like it's written, hit equals, and then divide it by the bottom to get the equals. most 4 red cards? What does that mean? I'm gonna write down what that means. What does that most 4 red cards mean?
Could be 4.
I could get 4 red, or I could get 3 red, or 2, or 1, or 0. Oh my gosh! Now remember, it was this or this in the last problem we did. You have a bunch of ors up there. So here's what I'm going to suggest you do. What if we did this? Oh wait, good. What if we did this? Can anybody tell me what I'm doing, what I'm thinking to do the problem this way, which is so much shorter than doing this? Max.
Is it because you're finding the probability to take
Well,
5 red?
this right here would be the probability of all red cards. Would that make sense to you? All red, there's 26. This is all red. In this problem, what I want is 0, 1, 2, 3, or 4 red. So the only thing I don't want is all red. Does that make sense to you? So if I can find this number, this is the probability of all red cards. I don't know what that is. Let's say it's 17%. If the probability of all red is 17%, then what's the probability of less than all red underneath?
83.
1 minus, absolutely. So we kind of refer to this as going in through the back door. Instead of adding up all the probabilities of what I do want, this is what I do want. I can do it, but it's like 5 problems in one. Instead of doing that, I take 100% minus what I don't want, and what I don't want is all red. So 100 minus all red would be easier, certainly shorter, than looking at all of these individual cases. All right, and finally, what is the probability of being dealt 2 of one suit and 3 of another? This is a tough problem, but I think you guys can figure it out. We want let's do an example. 2 diamonds and 3 hearts. Now, that by itself is not the answer to the question, but would you agree that's part of the answer? I mean, that's one of the cases we could have. So let's look at, what does that look like right there? What does just that look like? 13C2, nope, times, over 52C5. So this would be the specific probability of 2 diamonds and 3 hearts. What would the probability of 2 spades and 3 clubs look like? Same thing. And 3 hearts and 2 spades would look like the same thing, right? So this is essentially getting 2 of one and 3 of another. Now we just have to figure out how many of those combinations there are. Well, how many suits are there? 4. And I'm choosing 2 of them at a time. Now here's what makes this tricky. We're actually going to multiply this by 4p2. We do not use p's very often. But why does the order matter? What this is saying to me is, there's 4 suits, and the order I pick them matters. So it matters if I pick diamonds and then hearts, or if I pick hearts and then diamonds. Why does it matter? Exactly. They're different amounts. Just like, remember when we were picking people, if they were president and vice president, then order mattered. But if they were just a committee, it didn't. If this was 2 of each, then it wouldn't matter. But since 1 is 3 and 1 is 2, this is different than this. Those are different cases, agreed? So the order matters. So this is the basic probability of one of these situations. Instead of going through and figuring out all the possible situations, I'm just going to multiply by how many there are. And that is 4 and 2. Okay, that's hard. I'll give you that. That's a little tricky. All right. Now we've got some stuff that isn't so hard. Okay, so now we got some that's not so hard. Let's take a look at our Venn diagram. Now, you've all used Venn diagrams before. In fact, I was just subbing in a biology class last week, and I saw one laying on the teacher's desk. Something about carnivores and herbivores. So you understand how Venn diagram works, right? So if this was a ball for carnivores and this was a ball for herbivores, what would this little football here in the middle represent? Things that eat both, are they called omnivores? I don't know. They eat both? Okay. All right, so here we go. We have 30 students in the class. So I like to write the 30 up there. What that means is that box holds 30 people. Somebody has surveyed them, and the votes for M&Ms and Twix came in this way. By the way, today, this is Teacher Appreciation Week, and this morning the Mothers Club gave us all an emergency kit. It's full of candy to get me through the day. All right. How many kids like M&Ms? 17 kids like M&Ms. If you like M&Ms, you are in the M&M ball. All these people like M&Ms. 17. How many like only M&Ms?
11.
That's the 11. How many like M&Ms and Twix? 6. How many like M&Ms or Twix?
30, 20, 26.
26. Doesn't everybody in here like one or the other?
Yeah.
Some like both, and that's okay. But everybody in here likes M&Ms or Twix, so 26. How many like only M&Ms or only Twix? 20. How many like neither? 4. And how did you figure that out?
30 minus 26.
Exactly. There are 26 in the balls, 30 people altogether. There have to be 4 outside. All right, now you're going to make your own. All right, so here we go. 28 kids in the class. Everybody likes jazz or country or both. Everybody. So that means there's nobody out here. Everybody likes something. 18 students like jazz. So somebody took a vote, and 18 kids said they like jazz, and 14 kids said they like country. Do not put 18 here, because this doesn't say 18 like only jazz. But would this bother anybody? Even if you tried to do that, would that bother you? It should. How many people are in those circles?
32.
Well, that's 32. How many people are in the room? 28. Those are wrong. The whole 18. The whole country ball is 14. How in the world am I gonna figure this out? The middle's what? Absolutely. The middle's 4. How do we know the middle's 4? You already told me. There's 4 extras. That means those people voted twice. Now, if the whole jazz ball is 18, and 4 of them are in this part, then there must be 14 in this part. And if the whole C ball is 14 and 4 of them are here, this must be 10. Now, does that add up to 28 like it's supposed to? How many like only jazz? All right, a couple more Venn diagrams. Class of 32 students is surveyed as to the type of car they like. 19 like Fords, 19 like Buicks, and 12 like Chevys. Okay, so we're gonna have 3 circles here. So we have Fords, Buicks, and Chevys. 5 like all 3. So 5 go right here. 6 like only Fords. So would you agree I'm gonna put a 6 right here? 3 like only Buicks, and 2 like only Chevys. Now, in order to answer questions, we need to fill in the missing areas. I have no idea, and it doesn't tell me what these sections are. So for the time being, I'm gonna call them X, Y, and Z. I do not know what they are. But I do know that 6 plus X plus 5 plus Y has to add up to 19. Would you agree with that? And cleaning that equation up a little bit, X plus Y has to be what? 8, I think? 8? All right, let's do the next one. X plus 3 plus 5 plus Z has to also add up to 19. So X plus Z is 11. Keep an eye on my arithmetic, is that right? And then finally, Y plus 5 plus Z plus 2 has to be 12. So Y plus Z has to be 5. Now, what do you think I'm going to do now? You have a lot of options. First of all, remember how we learned how to do systems with 3 equations, 3 unknowns on our calculator? Don't you have 3 equations and 3 unknowns here, X, Y, Z, 3 equations? So if you want to set it up in a matrix format, you can. I think it's way easier to do an 8 set. I mean, these are simple little equations. So I'm just going to look at the first 2, and I'm going to eliminate the X. So what will that leave me if I take the first 2 and eliminate X? Y minus Z equals -3. And multiplied this one by negative and just added them together so the x's disappeared? Are you with me? Now, look at the bottom one. The bottom one says y plus z equals 5. Well, can I add those together? And it's going to tell me that 2y equals 2, so y is 1. And if y is 1, then x has to be 7. And if x is 7, then z must be 4. Now we can answer the question. Here we go. How many, or what is the probability that if a student is chosen at random, he'll like both Chevys and Buicks? So your denominator is going to be 32 because you're picking out of 32. How many kids in the picture like Chevys and Buicks? Now be very careful. It doesn't say only Chevys and Buicks. Aren't these kids right here, aren't these the ones that like Chevys and Buicks? They're the overlap of the C and the B. So how many kids like Chevys and Buicks? So your answer is 9 over 32. If it said like only Chevys and Buicks, then it would be 4. All right, reach in, grab a kid out of the class. What's the probability he won't like any of these cars? How are we going to figure that out? Add them up, subtract from 32, and see how many are hanging around out here. So let's see, I know F is 19, 22, 26, I got 28.
Yeah.
Is that right? So if there's 28 in the circle, that means there's 4 out here. So 4 over 32, which will 4 over 32, which we will reduce to 1/8. Everybody still with me, okay? All right, one more of these, one more. See, we'll get it started. Let's just see how much of this you can get done on your own. I think it looks like it's gonna be the same kind of thing. 68 seniors were asked if they like green, purple, and yellow. Green, purple, and yellow. Green was 43. Purple was 23. And yellow was 32. 6 liked all 3. Okay. Now, can you fill in? Where are you going to put the 11 that like only yellow? Here. And the 15 that like only green, and the 4 that like only purple. Okay, can't answer the questions until you figure out all these sections. So do you know what you're going to do? It's what we just did. We're going to assign them variables. We don't, doesn't matter what we call them. I usually do X, Y, and Z, but you can do whatever you want. So we got X, Y, and Z. And then what do? Set up some equations. So my green equation will be X 6 plus 15 has to add up to green, which is 43. So simplifying, x plus y needs to be, is that 20? Is that 22? Watch my arithmetic. And yellow is x and z and 6 and 11 is 32. So x and z is 15. And y and z and 6 and 4 is 23. So y and z is 13. Now, you go ahead and solve that. Go ahead and figure that out. Do it however you want. You do it the way we did the last one, which is, they always work out nicely when you do that. But you certainly, you have other options. Max and Eli, why do we not have lanyards on? Guys, infractions. Alright, anybody got these solved?
Yeah.
Looks like y minus z is 7 and y plus z is 13. Did you get y as 10?
Yeah.
And if y is 10, z is 3. And if y is 10, x is 12. How's that look to everybody? Perfect. What's the probability? Reach in, grab a kid, and he likes at least one color. So the denominator's 68, there's 68 kids. I'm gonna grab one. What's the probability he likes at least one color? What does that mean? Doesn't that mean he's in here somewhere? So we just add all those up. So we got 43 and 7 is 50. Did you get 61? Don't just nod. Jackson, did you actually add them up and get 61?
I got 60.
Okay, so the probability that he wouldn't like any color would be 7 68ths. The probability he likes something is 61 68ths. Everybody okay with that?
Yeah.
Now we have some more probability, or some more Venn diagram problems, but these involve probabilities. So instead of like people in the balls, we're gonna have probabilities in the balls. Very, very simple. This is the probability of A, liking apples, liking bananas. These would be the people who like both. So the probability you like apples is 0.6. The probability you like bananas is 0.2. And the 0.5. And the probability that you like both is 0.2. So this notation means I like apples and bananas. This is the intersection symbol, and both. This is both. So in terms of the Venn diagram, this is the 0.2. Those are the people that like both. This means and, apples and bananas. If the whole A ball is 0.6, then what's this section out here gonna have to be? 0.4. And the B's, likewise, this section is going to be 0.3. Now, remember how in this problem we just did, the whole thing adds up to 68? So as soon as you figured out these were 69, you knew there were 7 guys out here that didn't like anything? Well, this is a probability situation. What do all these have to add up to in a probability problem? 100%, 1, right? Well, how much do you have accounted for? 0.9, which means there's 0.1 out here. The box has to be 100%. What are these 0.1 out here? Those are the people that don't like apples or bananas. Okay, now let's answer the questions. We got some notation things going on. What's the probability of A and not B? That little hash means not. So this means I like apples, but I don't like bananas. So where am I? If I like apples but not bananas, aren't I right here? 0.4. This is, I don't like apples, but I do like bananas. That's these guys, 0.3. Remember, the hash is not, the upside down U is and, both. What's this? I don't like either one. That is 0.1. You guys on the outside of the circles? I don't like apples and I don't like bananas, so I'm out here. And the last one, another new notation, says what is the probability of okay, let me just write out what this says. This says what's the probability of A given B. So this is like red given. So this says what's the probability I like apples given I like bananas. And there's a little formula for this. The formula for this is the probability of A and B over the probability of B. So when you see what's the probability of something given something, the numerator is both, the denominator is the given. So you can answer this question easily. What's both? 0.2. What's just B? This is B. B is 0.5. So your probability is 2/5. They're right here, guys. They were just written right here in front of you. The probability of A and B over the probability of B. So what that means is, of all the people who like bananas, there's, let's say, 5 people who like bananas, 2 of them also like apples. 2/5. Alright, there's one more of those. Let's go ahead and do this next one. We'll do exactly the same thing, only now our letters are C and D, which doesn't matter. So now we have what? Cookies and donuts. And we know cookies is 0.75, donuts is 0.4, and both is is 0.35. So I'm gonna put my 0.35 right there where both are. All right, fill in the rest of your Venn diagram. You should be able to do it. Okay, so what'd you put over here? 0.4, 0.40 or 0.4, it doesn't matter. And what'd you put over here? 0.05. Yep, be careful on that one, it's gotta be 0.05. And then hopefully you added all this up and notice that it only adds up to 80%, 0.8. So that means the rest of the people are out here. Right? They don't like donuts or cookies. All right, does everybody have the Venn diagram down? You got it down? This is our last Venn diagram, so make sure you got it. Okay, now let's answer the questions. What does the first question mean? I hope I copied them right. The first question means, I like C, but not D. So that would be 0.4. What's this one? I like D, but I don't like C, so isn't that one 0.05? What's this one? Don't like either one, we already calculated that, that's 0.20. The probability of D given C, our formula says that's DNC over the probability of C. Okay, well we know that. What's DNC over CND? No one doesn't matter. That is 0.35. What is just C? No. I mean the probability of C, the whole probability of C. This is the whole C. So the whole C is 0.75. That reduces to something, I'm sure, 7/15. So remember, when we say the probability of C, we mean right there, the whole C. If we meant just that, we would have to say C but not D, right? Okay, almost done. 10A. If it rains tomorrow, the probability that Joe will do his homework is 40%. If it doesn't rain, the probability of doing homework is 10%. Given that the probability of rain tomorrow is 30%, find Joe's probability of doing homework. Okay. Okay, so there's like two sets of probabilities going on in this problem. Would you agree? We got some stuff about rain and we got some stuff about homework. We are going to use a tree diagram to answer this question. You've seen those before too. When you set up your tree diagram, first of all, determine what the two things are. We got rain and homework. Those are the two things. It's going to rain or not rain, homework or not homework. Whatever the question is, and the question is ultimately probability of doing homework, whatever the question is, goes on the bottom of the tree. So this is going to be rain and not rain. Whatever the question is, goes on the bottom. So the bottom is going to be homework and no homework. Homework and If it rains, he can either do homework or not. If it doesn't rain, he can do homework or not. So branch 1 is rain and not rain. And then we'll do the homework and not homework. Okay, let's fill in the probabilities. If it rains, right here, it's raining. If it rains, the probability Joe does his homework is 0.4. What does that automatically mean about this branch over here? 0.6. You gotta add that one. If it doesn't rain, the probability of him doing homework is 0.10, 0.10. Which means this one is 0.9. The probability of rain is 0.3, which means not rain is 0.7. How does that look to everybody? The question is, find the probability of doing homework. Now, Joe can do his homework if it rains, right? He can do homework if it rains, or he can do homework if it doesn't rain. Would you agree he can do it either way? Over here, it's gonna rain and he's gonna do his homework. Okay, so it's gonna rain and he's gonna do his homework. So guess what I'm gonna do with these two numbers? I'm gonna multiply them. It's gonna rain and he's gonna do his homework. The probability of that happening is 12%, 0.12. I multiply those because it is raining and he's doing homework. How about this one? What if it doesn't rain and he does his homework? Well, that would be 0.7 times 0.1 or 0.07. What is the total probability then that he'll do his homework? In other words, it's either this option or this option. The total probability is 0.19. Does everybody get why we multiplied these, but we added these? It's this or this. Well, that's enough for today. We'll finish this up next time. Tomorrow, I guess, we'll finish this up. So your 9-3 homework, I'll assign it tomorrow.